Hi guys, welcome to our first video on linear algebra. In this video, we're going to be looking at systems of linear equations in more than two variables. So, let's look at the objectives. So, these are the objectives for this video. So, we'll start by interpreting the solution of a system of linear equation in two variables. So, I'll just consider 2x plus y is equal to 10 and 3x minus 2y is equal to 1. Now the solution is x is equal to 3 and y is equal to 4. So we can substitute and you'll realize that those two values, so x and y, those satisfy the equation exactly. Alright, now what is this saying? What we're going to do is we're going to just do a quick drawing, a quick sketch of the line. Well, rather, I'm going to show the graph of the two lines. Now, if you note, both lines, sorry about that, both lines intersect at the point 3. So they intersect here. So they intersect at the point 3, 4. So where the y is 3, the x is 3, sorry, and the y is 4. So the solution for the system of the linear equation just represents graphically where the lines would meet. So on to the fun part. We're going to solve a system of linear equations using Gaussian elimination and Gauss-Jordan elimination. So Gaussian elimination, also known as row reduction, is an algorithm in linear algebra for solving a system of linear equations. Now, in order to do this, we need to rely on some row operations. So we have 3 row operations that we're going to depend on. So these will be in our toolbox. So we can swap position of 2 rows. We can multiply a row by a non-zero scalar. So we can multiply a row by a non-zero number, basically. And we can add to one row a scalar multiple of the other. So what this is saying is that we can multiply one of the row by some number and then add it to another row. Alright? And that will come in handy. So you might want to write off these row operations. So we'll jump straight into an example. So here we have a system of linear equations. So x minus 2y plus z is equal to 0, 2x plus y minus 3z is equal to 5, 4x minus 7y plus z is equal to negative 1. Now, the first thing that we need to do is we need to write the augmented matrix. To get the augmented matrix, we use the coefficient, I will keep them in the same order, alright? We use a coefficient of each variable. Now, if a variable is missing, we know that a coefficient is 0. If we don't see a coefficient there, we know that it's 1, right? So that will give us this part of the augmented matrix. And to get the other part, we rely on the answers. Now, we're going to start by using a Gaussian elimination. So to use a Gaussian elimination, the first thing we do is we ensure that this first term here is 1. If it is not 1, we need to make it 1. We can make it 1 by swapping rows or multiplying by some number to ensure that it is 1. In our case, in our example, it is already 1, so we're fine, we're good to go. The next step is to get zeros here, get these guys to be zeros. Now, how can we do that? What we're going to do is we are going to multiply. So if we multiply this 1 here by 2, that gives us 2. And if we subtract 2 minus 2, that is 0. So that's how we'll do it. Alright, so we're going to multiply the entire row though by 2. So we're going to multiply all of row 1 by 2. And then we're going to subtract that from row 2. Similarly, we're going to multiply all of row 1 by 4 and then subtract that from row 3. So our operations, row 2 will now be equal to row 2 minus 2 row 1, and row 3 will be equal to row 3 minus 4 row 1. And that is to ensure that we get 0 here. Now doing that gives us this matrix. Alright, so just a note, how did we get 5 here? Remember, row 2 is row 2 minus 2 row 1. So this is row 2, and we're going to subtract 2 times row 1 from it. So 2 times row 1, so 2 times 1, 2 minus 2, 0. 1 minus 2 times negative 2, that would be negative 4. So 1 minus negative 4, that's 1 plus 4, that will give us 5. Minus 3 minus 2 times 1, that's 2. So minus 3 minus 2 minus 5, and so forth. And through a similar reasoning, we can get the third row. Now, the next thing is we want this here to be 1. Now we could multiply by row 2 by 1/5 to get 1, but because we already have a 1 here, so if under the 5 we have a 1, so we have a 1 here, so we can just interchange these two rows because I want a 1 here now. So we swap row 2 and row 3, and that gives us this. So we'll just swap row 2 and row 3. Now we need this here to be 0. So how do you think we'll get this to be 0? If you said row 3 minus 5 row 2, then you would be correct. So doing that gives us this matrix here, and now our aim is to get this guy here to be 1. So we can just multiply by 1/10. So row 3 by 1/10, and that gives us this matrix. So now we have it in row echelon form, and we are now able to derive a few things. So just a note before we do that, a matrix is in row echelon form when it satisfies the following conditions. So 1, the first non-zero element in each row is called a leading entry, and it's 1. Each leading entry is in a column to the right of the leading entry in the previous row, and the rows of all 0 elements, if any, are below rows having non-zero elements. So you might also want to take off these. So the equations that we get are x minus 2y plus z is equal to 0. So how did we get that? We got that from the first row. So this one here goes with the x, so it will be x minus 2y plus z. So it's like 1x minus 2y plus z, and that is equal to 0. The second equation, so 0x, so that's a 0. We don't have any x here. Then 1y, which is just y, minus 3z, sorry, is equal to negative 1. So that's the second equation. And the third equation, we don't have any x, we don't have any y, so it's just z, 1z, which is z, is equal to 1. So let's proceed. So we know that z is equal to 1. So we'll right off the bat, we already have the value for z. From the second equation, we know that y minus 3z is equal to minus 1, but we know that z is 1. So we can substitute z as 1, and we'd get y minus 3,1 is equal to negative 1, and solving for y, we get y to be equal to 2. From the first equation, we know that x minus 2y plus z is equal to 0. We know that z is 1, y is 2. We make those substitutions, and we would solve for x, and we'd get x to be equal to 3. So the solution is x is equal to 3, y is equal to 2, z is equal to 1. Now we could go a bit further with the question. Alright, so that, remember where we stopped, that we call that row echelon form. Now we could go to what is called a reduced row echelon form, where we kind of take it a bit further. So let's do that. So as it is here, our matrix is in row echelon form. Now to get it in reduced row echelon form, what we want to do is we want to ensure that each leading entry, so the first term in each row is 1, but that's crucial for row echelon form. But now for reduced row echelon form, we need to ensure that there are only ones, there are only non-zero element in their column. So if we look at this one here, we have -2 here, which is a non-zero element. So we need to get this -2 to be equal to 0. And how do we do that? Of course, I'm sure you got it. We add row 2 times row 2 to row 1. Okay, so here this is just enforcing what I had just said. So we have 2 times row 1 and, well, actually what we want to do is, I mean, could have done that, but to make our lives a little easier, we make these two be equal to 0 first. So this is just 3 times row 3 plus row 2, and this is just row 1 minus row 3, right? And that gives us 0, 0 here. So now we want this here to be 0, and it would be row 1 is equal to 2 row 2 plus row 1. So now we have it in reduced row echelon form. And once again, we can get our equations. So we have x to be equal to 3, we have y to be equal to 2, and we have z to be equal to 1, which is the same solution that we got earlier. So that is the end of our first video on linear algebra. You might want to rewatch the video just in case you missed anything.